Red, wonderful, and also happy Monday, right? Okay, so I don't know who has not joined. I can see George. Um, I received that is some apologies from Chacha. He won't be joining today. I think it's George. George. Yeah. Okay. But anyway, we can start. He will catch up. So let me share my screen so that we may continue from where we left. Okay. Yeah, I can see George is in. Okay, good. Last time we discussed or we introduced regression analysis, and we covered some content that is in our slides. We talked about different types of regression. We talked about. Did we talk? Yeah, I think we did not talk about linear regression line. Did we talk about this? I don't think if we talked about it. Types, of course, types of regression we discussed. We discussed about. Yeah, I think we should be here. Okay. Okay. So we are going to start here. Okay. So I want us to start with the linear regression line. And of course, I know you talk about, when we are talking about regression line, you know what it is because I did an illustration of the graph where we, we defined some of the variables and also, in fact, we used the straight that is the equation of straight line as our simple linear regression model. Okay, so just to illustrate, let's assume this is our graph. We have some data points. Okay, let's assume we have some data points. Okay, and then we have a line of best fit. Okay, we have line of best fit. So this is what we call a regression line. This is what we call regression line. Okay. Yes. And this regression line can be of two types. Okay. We might have a positive linear relationship, that is, or the line might be having what? A positive linear relationship to the variables, that is the y and x, or it might have what? A negative linear relationship. Let's, for example, take an example of this line. So, example of this line, first of all, it is a positive. Uh, it has positive relationship. Okay, why? Because you can see from the graph. Let me just say this. Let's say this is 10. We have 20. Okay, we have that. Okay, and here we have maybe, let's say, 5, we have 10, we have 15, okay, and we have maybe 20. Okay, so a positive relationship, okay, we said that is the variable should be moving in the what? In the same direction. Okay, the variable should be moving in the same direction. Like if one it is increasing, then the other value should be, the variable should also be increasing. Okay, like for example, if we increase x, what is happening to that is y? Can someone tell me, if we increase x value, okay, what will happen to the y value? Will it increase or it will decrease? Like for example, let's take the value of y when x is what? Is 10. So when x is 10, we have, yes, Bill?
Yes, good evening.
Good evening.
Uh, I think when we increase the value of x
Mm-hmm,
for the positive linear relationship,
mm-hmm.
then the value of y increases.
Of course, that's very correct. So for positive linear relationship means that when one variable is increasing, so does the other variable. Okay, like for example, the value of that is the value of y when x is what? Is 10. We can say it is also 10. We can just assume it is also 10. Then the value of y when now we increase x from 10 to 20, of course you can see it will be what? It will be a higher value, maybe 20. Okay, so you can from that is from this we can say that as the value of x increases, the value of y is also increasing. So we have what? We have a positive relationship. Let's take now the second scenario. Let me do the second scenario. So we have now the second scenario, and we are saying that, of course, if that is for negative linear relationship, when that is when one variable is increasing, the other one will be reducing. Okay, like for example, as we increase x, that is the value of x, the value of y will be decreasing. So we can say, let's assume at this point, of course, um, I want to do an example that is a good example. We have this, we have this, we have this, we have this. Then I will do what? Sorry. I want to do that is equation of all to do the line of best fit. Let me first of all just do it. Can say this is the line of best fit. So you can see. So you can see as the value of what? Of x is increasing. X is increasing. That is at this point. Okay. So as the value of x is increasing, the value of y it is decreasing. You can see this distance. Remember y it's now this deviation. That is, this is what we are measuring. This deviation. It is what? It is our y. So you can see our y. So you can see As we increase the value of x, okay, our y value is what? Is decreasing. Okay, vice versa. If maybe we are reducing the value of x, then the value of y, it is what? It is increasing. So with this now we will have what? We will have a negative relationship whereby one variable is increasing as the other variable is decreasing. So those are the examples of two linear relationship in regression. Okay, so let's maybe summarize this with the notes here. So we are saying that a linear line showing the relationship between dependent variable and independent variable, it's called what? The regression line. Remember, our independent variable, it's what? It is x. Then our dependent variable, it's what? It's y. Like the example of this model is equals to y is equals to m, or let me just do a better model. So let's assume we have umbrella cells. Umbrella cells, let me just use abbreviations. So we have umbrella cells is given by rainfall amount. Okay, sorry, we have a constant multiplied by rainfall amount. Let's say a constant of a. Then rainfall amount, we can call it what? We can call rainfall amount x. Okay, x is what? Rainfall amount. Then plus what? Plus another constant. Remember, we said that this is our output. It's what we are trying to predict. Okay, then it's a constant, and when we are using that is the equation of the straight line in a graphical presentation, we said a is what? Is the slope or the gradient. Then for C, we said it is what? For C, we said it is the y-intercept. And also we usually add in our models, we usually add what we call error term. That is epsilon. Okay? Whereby epsilon is what? It's our error term. It's also called residuals. And also it's also called that is vertical deviation. Like for example, if I have some points here which were not within our regression line, so of course now this vertical deviation, it's what? It's what we call error term. Okay, so the difference between the regression line and the that is the value of what? Of y in this value, it's what? It's our it is our in deviation or y deviation. Yeah. So that was just a by the way. So this is maybe our model. Okay. Yes. So and you can see we have independent variable, which is our x variable, and then our that is our dependent variable, that is our output. So we can say that positive relationship, that is it's when or happens when like if the dependent variable increases on the y-axis and independent variable also increases on the x-axis, then such a relationship is termed as a positive linear relationship. Very true. I illustrated that. Like when one variable is increasing, the other variable is also increasing. Then for negative linear relationship, if the dependent variable is decreasing along the y-axis, then independent variable is what? Is increasing on the x-axis. That is, this is the relationship. As y is decreasing, then x is what? X is increasing. So with that, we will say that our relationship between these two variable, it is negative. Okay, good. How do we find the best fit line. Okay, that is, how do we get this the best fit line? Like for example, let me do an illustration. So we have these data points. Let's assume we have these data points. Okay, let me redo that. Okay, let's assume we have some points which are running, that is through this line. Okay, or most of the points are running, are running through this line. So the best fit line, it's when most of our what, most of our data are within what, are within the regression line. Okay, so if we are, or if we have, that is our data points more close to the what, more close to the regression line, of course we will have what, we'll have, that is a good, that is fitness of fit, or that is best or goodness of fit of our line. Why? Because this shows the percentage of, that is the percentage of data which is covered, that is within this regression line. Okay, yes. So I think we are good in that. Okay, so now we can maybe get through the notes and see um, what the notes are saying. So when working with linear regression, our main goal is to find the best fit line. That means the error between the predicted and the actual values should be minimized. The best fit line will have the least error. So, like for example, you can see that is our error term. That is our error term will be like the addition of what, the differences between the actual values and these values. You can see the values with that is which are outside the regression line. Okay, so like here we will get, that is this value minus this value, that is the vertical deviation. Okay, so if you had all those vertical deviations, you will get what we call sum of error terms. Okay, so if the sum of error term, it's a small value, then it will mean that you will have a good model. Okay, but let's assume maybe compare this regression line and this one. Okay, let's assume we have, this is the regression line. Okay, of course we have some points which are running through, but we have now other error terms, or other data points far away from the regression line. So you can see now the deviations of these points will, it's what, they are very large. Okay, just to say. So meaning our error term will be also high. And then we will say this model, it's not good fit for our what? For our data. We usually say the best model should fit 98% of what? Of our data. Okay? We shall see that when we'll be doing practicals. So we usually say that that is the best model fits maybe 95 or 97% of our what, of our data. So now, in case we have such model, how can we optimize this model so that we may have a statistical significant that is a model? So now here we'll come to that is optimizing. There are two different methods. Optimizing, that is the coefficients of that model, which is under the cost function. But we shall come to that and see how we can improve, that is the performance of our model. So We have different values for the weights, or what we call coefficients of the what, of the lines. Like for example, A and C are what, are coefficients of our what, of our model. Like for example, let me take a model. Let's say we want to that is predict the salary, okay, given we have what, or using experience, or using work experience in years as our what, as our independent that is variable. So of course we'll have what, our coefficient one. Let's just use this to denote coefficient which is attached to x variable. So it will be coefficient 1 multiplied by x plus coefficient 2. Okay, so you can see we have now these coefficients. These are our coefficients or our weights. Okay, yes, so that's what we are talking about here. So the different values for weights or different or coefficient of the lines gives a different line of regression. So we need to determine the best value of this coefficient. So we have to optimize this point, that is these values, to get the best values. Okay, and to find the best fit of the line, we calculate what we call cost function. Okay, and what is cost function? So let's talk about cost function. So the different values for weights or coefficient of lines, that is a0 and a1. These are our coefficients. Gives different line of regression, and the cost function is used to estimate the value of the coefficient for the best fit of line. Basically, cost function optimizes the regression coefficients. Okay, so this method optimizes the, that is the coefficients or the weights of our model, and it measures how linear regression model is performing. Okay, yeah, so this is also a method of examining how your model it's what, it's working. Then we also have different cost functions. Like for example, um when in regression we usually use mean square error as our cost function. Even when you will be that is studying more about that is machine learning, you will see how you can use mean square error, mean squared error, to what, to optimize your model. Okay, yes, so we can use the cost function to find the accuracy of the mapping function, which maps the input variable to the output variable. So this mapping function is also known as hypothesis function. Now, the hypothesis function is the mapping function. Okay, and basically it's used to show that is the accuracy by mapping the input value, that is variable. Okay, by mapping or by what it does, it maps like this is like the constant, whereby it is being mapped with the input function or the independent variable. Okay, in order to have what, in order to get that is an optimal output variable. And we are saying that for regression, for linear regression, we use the mean squared error cost function. Okay, which is the average of the what, squared error that occurred between the predicted values and the actual values. So the that is the cost function or the squared mean error is given by what, is given by that is average of, it is given by the average of squared error that occurred between what? The independent, the predicted or the dependent and the actual values. Like for example, now it will be summation of, okay, xi's. Xi's, they are what? They are our actuals, okay, minus the predicted. Okay, that is the actuals minus the predicted. Like we have the formula here, and then of course, sorry, we are talking about the average, so you have to divide with what? With the n. And remember, our y at is equal to what? Our y at is equals to a of x plus what? Plus b. This is the constant. Okay, of course. Why? Because if you get these values, or if you have this value, you will get the predicted value of what? Y. Okay, like for example, let's assume we have 0.5 as our what? Constant. So multiply by x plus what? Plus 10. Let's assume y is 10. What will be the value of what? Our y. So the value of our y will be of course 15. And this is our, it's a what? It's a predicted value. Okay, that's now we want to say that now the mean squared error, that is the mean squared error, will be given by, or will be equal to, that is summation of yi's, okay, minus into now this, because we said y at is equals to this, so it will be into a x plus b, then divide by what? Divide by n. Yes. So this is what? This will be our mean squared error. That is, if you are now, we are now to do the mathematical calculations. So let's go to the next slide and see that. Okay, we forgot something. That is, we should be square, because it is mean squared error. Okay, mean squared error. So we have to square our error. So we will have to square our error term. Okay, so this will be what? This will be our cost function. In, if maybe you are using population, now this will change to capital N. Okay, let's now continue. So for the above linear equation, that is mean squared error can be calculated as this. You can see this is the formula which we've just written. It's just because they have that is factored out the what? The one divide by n, but it is the same concept. Okay, whereby n is the total number of observation. May it be in a population, or may it be in what? In a sample data. Okay, may it be in a population or in a sample data. Then we have y I. Yi, it is the actual observations, or the actual value of the observations. Then this one will be what? Will be our predicted, that is value, our y at. Okay, it is our predicted variable, that is value. Then we have the residuals. Okay, that is the residuals. That is the vertical deviations. Okay, or the difference between, that is the it is like we are trying to check the distance between what? Between the scatter points, or our data points, and the values within the regression line. So the distance between the actual, or basically you can say this, the distance between the actual value, and the predicted value, it's called residual, or the error term, or the vertical deviation. So if the observed points are far from the regression line, then the residual will be what? Will be I. That is, like, for example, give me a minute, I connect my PC. Just a minute. Okay, let's continue. So, uh, we can see if the observed points are far away from the regression line. Like, for example, the example, that is the example I had given. Okay, so of course we have some points along regression line, and then we have these points, these data points. Okay, so we are saying that if the observed points are far away from the regression line, so you can see we have, that is a very that is a big distance, okay, between what? Between these points and the regression line, okay, and the regression line. So of course the error term will be, or our residual will be what? Will be very high. That's why we are saying if the observed points are far away from the regression line, then the residual will be what? Will be high. So the cost function will be what? Will be also high. And if the points are scattered close to the regression line, that is, if maybe the points are within the regression line, okay, let's say they are almost along the regression line, then we will have what? We'll have that is small error term, okay. And if we get the small error term, then it means we have what? We have small cost function. And if we have small cost function, okay, the better your model. But if we have high cost function, then your model, it's what? Is very poor. Okay. When in terms of performance, it will be very poor, and its accuracy will be even below what? Will be below 50%. So error terms also help us to determine the goodness of it. We shall also see that when we'll be dealing with the practicals. Okay, what about gradient descent? Before I can go to gradient descent, any question up to that point within those slides? Maybe someone might be having a question, or someone may need clarity. Yeah, you can ask. You can ask, or you can also do an addition. Okay. Okay, now then we can continue. Let's now continue if no question. Let's now talk about gradient descent. What about gradient descent? Okay, so now gradient descent tries to optimize the cost function, or it tries to find the best, that is the best value of the cost function, or it tries to minimize the cost function. And if we minimize the cost function, we will have that is optimal value of our values of our what, of our constants. And if we have optimal values of our constants, then we will have what, we will have a better model, or our model will be what, will be very very good model. Okay, so now check out this. Gradient descent tries to that is optimize, or it tries to find the smallest value of the, or to minimize, it tries to minimize the value of cost function. Okay, then this minimum cost function, if we get minimum cost function, then it means our constants are what, that is, this is the first constant, and this is the second constant, meaning this constant or coefficients will be what, will be at their optimal point. Okay, so if these are have the optimal value, then we'll have a good regression line. Okay, or best fit regression line. Okay, yes, so let's now do a deep dive on the gradient descent. So for gradient descent, it is used to minimize the, that is the mean square by calculating the gradient of the cost function. A regression model uses gradient descent to update the coefficients of the line by reducing or by minimizing the cost function, and it is done by a random selection of values of the coefficient, then iteratively update the values to reach the minimum cost function. So this is done randomly. That is, it's like you are it is like a scenario analysis. Okay, whereby under a scenario analysis, you are randomly choosing what, you are randomly choosing that is your coefficients. Okay, and the coefficients which will have the lowest what, the lowest the lowest cost function, then we will say those are the best coefficients to use. Okay, in our regression model. So with that, we are what, we are now using gradient descent to find the minimum or the minimum cost function in order to improve that is the performance of our model. Okay, then what do we call, what is this we are calling that is model performance, or how do we determine the performance of our model? So we usually have some statistical methods which can be used to determine that is the the equation, or that is used to determine the good what, the good model. Okay, yes. So let's start. So the goodness of it determines how the line of regression fits the observations. Okay. So the process of finding the best model out of various model, it's called optimization, and it can be achieved by the method below. That is R squared. R squared. Okay, we have R squared. Now, this R squared is also known as coefficient of determination. It's also called coefficient of determination. We shall also meet another value called adjusted R squared. But this will deal when we'll be doing the practicals. Okay, so tomorrow we are going to do basically practicals of on what, on the regression analysis, because today we are going to cover the theoretical part of it, and then tomorrow, now we will do what, tomorrow now we will do the practicals. Okay, then after that we'll go to that is to the almost the last topic of the statistics class, that is Distribution with what? Inferential statistics. Okay, distribution combined with inferential statistics. So that will be our last topic. Anyway, let's continue. So for adjusted R squared, this is majorly used when we are dealing with multiple linear regression. When we are dealing with multiple linear regression, it's when we use adjusted R squared. But for simple linear regression, we are just going to use what? The R squared. Okay. Yes, we shall calculate that. Then, what is this R squared? So, R squared is a statistical method to determine the goodness of fit. Now, of course, if we get the best goodness of fit, okay, then it means we have what? We have a good model. Okay. Yes. So, R squared is used to determine the goodness of fit. The measure it measures the strength of the relationship between the dependent and the independent variable on a scale of 0 to 100. Okay. Yes. So the I, the value of R squared, the less between the predicted values and the actual values, or the less the error term. Okay. Less the error term, the error term. Okay, so less the error term. So because you can see here we are taking the difference between predicted values and the actual values. Okay, or it might be either way. You can take the actual values minus the predicted value, and then of course if you square, you will get an absolute value. Okay, you will get a positive. Even if this value is greater than this, you will get what? You will get a positive value, because let's say negative 2 squared, it is 2. All right. So hence we are saying that the r squared determines the less what? It means if we have I r squared, it means we have less error term. Okay, and hence this represents what? A good model. Okay, so that's why at the beginning of the course I said that the small that is standard error, or the sum of error, or the error term, can be used to do what? Can be used to determine the goodness of fit of what? Of a model. Okay. So it is also known as, or it is also called coefficient of determination, or coefficient of multiple determination. That is, this is for multiple linear regression. This is for what? For simple linear regression. And of course, we have a formula to calculate this. Yes, we usually have a formula to calculate this. I don't have the formula here, but I will also share the formula when we'll be doing that is the practicals. Okay. Any question up to that point before I can or before I can go to assumptions of linear regression? Because I want us to cover that is the assumption of linear regression, and then we'll talk about that is preparation of data for regression analysis, and then from tomorrow now we'll go to the practicals. Okay, from tomorrow we are going to the practicals. Any question up to that point? Any question? Okay, it means we are all good. The class is getting everything right. That's wonderful. Okay, let's go now to assumptions of linear regression. Okay, so we have very important assumptions to take in consideration when you are dealing with linear regression. And the first assumption, in fact, I've been stating this almost on daily basis. That is, there must be a linear relationship between your features and target variable. Okay, features, they are x variables. Maybe it can be one x variable or more x variables. Okay, and then our target is our y. This is our output. These are that is our inputs. Okay, so there must exist a linear relationship between the in the dependent variable and independent variables. Okay, yes, so in fact this we can put that is, it can be dependent variable and independent variable. That is for simple linear regression, or dependent and independent variables for multiple linear regression. Okay, okay, good. So that is our first assumption. Okay, yes. Then the second assumption is that we should have small or no multicollinearity. This basically means we should not have any high correlation between what? The independent variable. Let's assume we have two independent variable, okay, which are used to predict what? One dependent variable. Okay. So we should not have any relationship, or we should not have any high correlation between these two variables. Okay, why? Because it will be difficult to know which factor or which independent variable is affecting y, or it's affecting what? Our output. Let's take an example of salary. Let's say y, it's our salary, and we are using salary. Okay, that is, we are using work experience. So x1 is what? Work experience. Okay, to determine what? To determine that is work experience, and our second variable, that is 2, will be what? Will be, that is x2, will be maybe skills. Of course, we know work experience comes with what? With skills. Work experience comes with skills. Let me put an error term here. So let's say if we are quantifying work experience in years, and also quantifying that is skills you have in terms of also years, okay, then it might be difficult for us to know which value or which variable between work experience and skills is affecting what? Is affecting that is our output, or it's affecting the salary. Okay, yes, that's mean we have high correlation between work experience and skills. Okay, so that's why we are trying to say we should have very small or no multicollinearity, or no correlation between these two variables for us to be able to know which independent variable is affecting what? Is affecting our output. Maybe we can go through the notes. That is, multicollinearity means high correlation between the independent variables. Okay, and due to multicollinearity, it may be difficult to find the true relationship between the predictors and the target value, or we can say it is difficult to determine which predictor or which independent variable is affecting the target variable and which is not. Okay, so it will be difficult for us to know all those things. Okay, So our models, or it's good for linear regression to have little or no multicollinearity between the features and the independent variables. That's all about multicollinearity. We should have small or no multicollinearity. Okay, good. Now let's go to the third assumption, that is homoscedasticity. Okay, that is homoscedasticity assumption. And now this assumption that is tries to mean that we should not have any relationship between what the error terms. Okay, we should not have any pattern, any clear pattern between the error terms. Okay, that's what it is trying to say. Or we should not have any clear pattern or any uniformity in our error terms. So homoscedasticity is the situation when the error term is the same for all the values of the independent variables. With homoscedasticity, there should be no clear pattern on the distributions of that is distribution of the data in the what, in the scatter plot. Like for example, we should not have like the data it's trying to that is to have a specific pattern. Okay, like this, you can see with this, you can see we have like a specific pattern. Okay, within what, within our data. So you can see with this we can see a clear pattern within what, within our, that is our data points. Okay, but now the opposite of homoscedasticity, it is heteroscedasticity. Okay, whereby now our what, our, that is our error terms are what, distributed all over. You, it's not clear, you can't find any that is specific what, pattern in what, in the distribution of our data points. It's like our data points are distributed all over. Okay, yes, so that's all about this that is assumption. That is, now we should not have what, we should not have any clear pattern between what, between that is our data points. Then we have normal distribution of our error terms, or our error terms should be normally distribution. Okay, our error term should be normally distributed. And how do we do so? So linear regression assumes that the error term should follow the normal distribution pattern. Like if error terms are not normally distributed, then the confidence interval will become either too wide or too narrow, which may cause difficult in what, finding the best coefficients. So that's why we are saying that the, that is the normal that is the error term should have what, should follow a normal distribution. Okay, that is, they should be normally distribution. Then we have no autocorrelation. Okay, don't confuse autocorrelation with the correlation. Okay, that is with multicollinearity. Okay, don't confuse autocorrelations with multicollinearity. Now, when we talk about autocorrelations, we are talking about that is a correlation within the error terms. Okay, that is like we are talking about that is the error should not be autocorrelated. So linear regression model assumes no autocorrelation in error terms. If there will be any correlation in the error term, then it will drastically reduce the accuracy of the model. So our error terms should not be correlated in any way. Okay, our that is our that is our that is our error terms should be not, or should not be correlated in either way. Otherwise, if it does, it will now bring dependency between the residual errors. And with this, it will reduce the accuracy of the model. So autocorrelation usually occurs if there is dependency between the residual errors. So if we have dependency in the residual errors, then we'll have high autocorrelation. And we should not have that is autocorrelation for us to achieve what? To achieve a more accurate model. Any question on the assumptions? Any questions on the assumptions before I can go to the last that is point or the last slide of our today's class? Any question? Okay, then it means we are all good. We've understood that is the assumptions of linear regression. Now, preparing data for linear regression. Okay, how do we do so? How do we prepare that is data for linear regression? So, linear regression it's been studied at great depth or length, and there is a lot of literature on how data must be structured for us to make use of the best model or to get the best model. So as such, there is a lot of sophistication when talking about these requirements and expectations, which can be intimidating. So, like for example, in practice, you can use these rules more as rules of thumb when using ordinal list um, square squares regression. So, but basically, we want what we want the that is the uh, the methods or the process of preparing the data for linear regression. So we have the first one. We should have a linear assumption or we should have a linear relationship between the two variables, okay, which you want to use them to maybe to create a predictive model. Okay, yes, so there must be a linear relationship. If we don't have any linear relationship between your two variables, then that is your model can't or your variables can't be used in what? In the regression analysis. So linear regression assumes the relationship between your input and output is linear. It does not support anything else. This may be obvious, but it is good to remember when you use a lot of attributes, you may need to transform that is your data to make that is the linear relationship or to make your data to follow a linear relationship. And these are examples of transformation which you can use. You can use log transformation for any exponential what? Data related. Okay. If your data or if your variables are exponentially related or distributed, then you can use log normal now to convert what? To convert that is like for example, let's assume y is exponentially distributed. So it is exponentially distributed. So that is we have a exponent of negative x, then plus a constant. Okay. Yes. So if we want now, this is an exponential what? This is an exponential uh, kind of relationship. Okay. So if we want to do what? To make this relationship be linear, of course we'll find the log of what? The log of y is equals to log of e raised to negative x um, plus what? Plus c. And with this, you will always get what? With this, you will now get log of y will be equal to that is x multiplied by x multiplied by log of that is e raised to maybe negative any value. Okay, let's say negative 1, then plus c. So with this, you can see this will be a constant. This will be a constant. Sorry, plus log c. This will be also constant, but you will what? You will vary your variables. Okay, so this is how you can transform. That is a log what? A log exponential relationship to a linear relationship, that is using log transformation. You can go and research more on this transformation, that is transformation of law that is of exponential relationship to a linear what? To a linear relationship. Okay, that's our first assumption. Then let's go to the second assumption. The second assumption is very simple and direct to the point. That is, remove noise or remove outliers. Okay, noise, it's what? They are outliers. Okay, so noise is an outlier, or we can call them extreme values. And you know, these extreme values can be extreme low or extreme high values. Okay, so you have to remove those outliers. So linear regression assumes that your input and output variable are are not noisy. Consider using data cleaning operations that let you better expose and clarify the signal in your data. The most important for the output variable, and you want to remove outliers in your output variable y if possible. So you have to remove what? You have to remove the outliers. Then remove collinearity. Remember, we said that we should not have what? That is features which are highly correlated. Why? Because they might overfit your data or underfit your data. Okay, so remove collinearity or remove the features which are highly correlated. So linear regression will overfit your data when you have highly correlated input variables. Consider calculating pairwise correlation for your input data and removing the most correlated what? You have to remove the most correlated features. Okay. Yes, so that's another that is a method or another step. You have to remove the collinearity within your independent variable. Then we have Gaussian distribution. That is your error term should be. You should make sure that is your error term are what? Are following normal distribution. Okay. Yeah, they are Gaussian distributed. Normal distribution is also another, that is another name of Gaussian distribution. Okay, so Gaussian and normal, they are the same thing. So for linear regression, will make more reliable prediction if your input and output have a Gaussian what? Distribution. You may get some benefits using some transforms like log normal transformation or Box-Cox transformation on your variable, okay, in order to attain a Gaussian distribution. Then we have rescaling of your inputs. Of course, it is good to rescale your inputs in order to get a more a more accurate, okay, or a more standardized what a more standardized prediction. So linear regression will often make more reliable prediction if we rescale the input variables using standardization or normalization methods. Okay, so these are some of ways how you can prepare your data before now you do what before you can do now the regression analysis. Okay, so those are the few steps is of preparing that is data for linear regression. Okay. Okay. Any question up to that point? That's the last that is slide for today's class. The other things we've already discussed, that is the correlation analysis we've already discussed. Okay. That is about the positive correlation and negative correlation. We've already discussed this. Then we have coefficient, that is correlation coefficient. Of course, we remember us doing the number line. Okay, remember us doing the number line. So that is to make insights, like for example, if you get that is values less than 0.5, you know that is your relationship. Okay, the way it is. Okay. Yes, so correlation coefficient, we had discussed that, and we said for your correlation should be within what? Should be within 0 and 1. Anything more than that, it is what? Um, you are wrong. You have to recheck your approach. Any question up to that point? Any question? Any comment? Any suggestion? Okay, then it means we are good. It means we are good. Then we can have, that is, you can enjoy your night and then meet tomorrow. Tomorrow we'll be now doing purely that is practicals, so that we may